All right, today we're going to tackle one of the most essential graphs in all of precalculus, the logarithmic function. Now, I know it might seem a little abstract, maybe even intimidating at first, but trust me, by the end of this, you'll see it's not just manageable, it's actually incredibly powerful.
Okay, so let's just dive right in. The absolute secret to understanding logs is to realize they're just the inverse of exponentials. Think of them like mirror images of each other. So what does that really mean for their graphs? Well, it means all their key features just trade places. You know how an exponential function, y equals b to vx, flattens out against that horizontal line at y equals 0? Well, for its inverse, the logarithm, you just swap the x and the y. And just like that horizontal boundary becomes a vertical one at x equals 0.
So how do we actually draw one of these things? It all starts with a super simple blueprint. Seriously, you can forget about memorizing dozens of points. There are just two essential rules you need to nail down for the basic parent graph, and they work every single time. And here it is, y equals log base b of x. This is what we call the parent function. It's our starting template, our ground zero. Every single complicated log graph you'll ever see is just this basic shape that's been shifted around, stretched, or flipped. You master this one, you can master them all. It's that simple. So let's talk about rule number one. This one is absolutely crucial, the vertical asymptote. For the parent function, this is always the line x equals 0, which is, just the y-axis. Think of it like an invisible electric fence. The graph is going to get incredibly, infinitely close to it, but it will never, ever touch or cross it.
And rule number two, this is your anchor. Every single basic log graph, I don't care what the base is, will pass through this exact same point, the x-intercept at 1, 0. Now, why is that? Well, just think about it for a second. Anything to the power of 0 equals 1, right? So this point is your guaranteed starting place. It's the anchor you use to sketch the entire curve.
All right, now for the fun part. Let's take that simple blueprint, our asymptote and our anchor point, and see what happens when we start moving it around. This is where we get into transformations, which is really just a fancy way of saying shifting and flipping the graph. So let's try one out. How would we graph something like f of x equals log base 2 of x minus 3? See that minus 3 tucked inside the parentheses? That's our big clue. It's telling us something is about to move. It's a really simple 4-step process. Step 1, find your new asymptote. All you do is take whatever is inside the parentheses, in this case x minus 3, and set it to 0. That gives us x equals 3. Boom. Step 2, draw that new boundary line. Step 3, shift your anchor point. Our original point was 1, 0, right? We just move it 3 units to the right so it lands on 4, 0. And finally, step 4, just sketch that classic log curve right through your new anchor, making sure it gets closer and closer to your new asymptote. Okay, shifting makes sense. But what happens if we see a negative sign show up? Let's take a look at a function like f of x equals negative natural log of x. That little negative sign sitting out front completely changes the graph's direction. This is what we call a vertical reflection. Because that negative is on the outside of the function, it literally flips the entire graph over the x-axis. So instead of rising up towards positive infinity like it used to, our graph now dives straight down towards negative infinity. The asymptote and the x-intercept, they stay in the exact same place, but the whole curve is now a perfect mirror image. All right, now that we know how to graph these things, let's talk about some practical advice. We're going to look at the single most common mistake students make, and then we're going to see why this isn't just some random classroom exercise. It's actually a super powerful tool for understanding the real world. A question I get all the time is this. As the graph dives down along that vertical asymptote, where does it finally stop? I mean, it's got to end somewhere, right? The answer? It doesn't. And this right here, this is the single biggest conceptual trap. You have to burn this into your memory. As the quote from Baker's math class says, the graph gets infinitely close, but never touches the asymptote. It's a boundary that defines the function's behavior off to infinity, not a brick wall where it just stops. So why do we care so much about these strange, infinitely approaching curves? Well, because they have a kind of superpower. And to see it in action, let's take a look at something from the world of computing called Moore's Law. Moore's Law basically says that computing power grows exponentially.
Now, if you plot that growth on a standard graph, you get what people call a hockey stick curve. It just shoots up so ridiculously fast that it's almost impossible to read or to predict where it's going next. It's just explosive and confusing.
But watch what happens when you plot that same exact data on a logarithmic scale. That chaotic, unpredictable hockey stick curve transforms into a perfectly straight, predictable line. This is the magic power of logs. They tame explosive growth, they reveal the hidden patterns, and they let us see into the future.
Which kind of leaves us with this final mind-bending thought. We know the graph extends infinitely downwards along its asymptote. Well, later on in calculus, you're going to learn that the area trapped between that curve and the x-axis can also be infinite. So it makes you wonder, if a simple log graph can contain an infinite area within its curve, what other hidden infinities are logarithms waiting to help us see?